we shall begin. Welcome everybody to ITALO, and thanks Rudy for popping the link in the chat. We are a special interest group focused on improving transparency around linkage outputs, and we've been running these webinars to increase awareness and knowledge sharing about linkages, new methods, novelties, but also in communication, and how can we share knowledge in a way such that we can, well, allow the thriving community to grow. And today we are very excited and honored to have Sumayya traveling all the way from Australian National University to come and give us a talk in person and online to our online audiences. Sumayya has rich experience in record linkage and PPRL and has been an absolute pioneer in developing new methods around quality assessment, linkage quality, and PPRL methods. So I'll pass time over to Sumayya.
Thank you. Thanks, Joe. A very good afternoon to all of you. When we originally spoke to Joe and asked him if he could do this, he said there's going to be very few people. Clearly, Joe has a different definition of very few. But it's nice to be here in London. It's actually my first time in London, and it's also nice to meet a lot of you all in person. Some of you on call, I think I've met before. So quick hello to everyone. So as Joe mentioned, I am Sumayya. I am a PhD candidate attached to the School of Computing at the Australian National University. I work in record linkage. My research specifically focuses on developing privacy-preserving record linkage techniques. So today, I think I'm stepping back a bit and exploring a broader context of record linkage. I'll be looking at some of the work that our lab has been doing on different aspects of record linkage that's not specific to PPRL. For those of you who've been at IPDLN, as Joe mentioned, some of this must be familiar. But after going through a long thought process, we decided that we'd speak about 3 specific studies that we've been working on within our team. The first looking at how different string similarity functions work on different ethnic groups and how that affects linkage. Secondly, looking at a novel performance measure, evaluation measure for evaluating record linkage outcomes. And thirdly, a bit of introduction to some work we have been doing with the University of Edinburgh and the SHIP project, the Scottish Historic Population Platform project that I have been working on for a couple of months, where I've been presenting what we've been doing on linking vital life events to census data.
Sorry, Sumayya, we don't have the slides online.
Oops.
Oops.
Sorry.
Sorry to interrupt.
Let me see. Does that work?
Yes, thank you very much.
Awesome. Thank you. So all of this work, we've been collaborating with different people around the world. Peter, I work very closely with Peter, who is also my primary supervisor and is here today. We've also been working with Rainer from Germany, Joe. We've been collaborating with Joe since, I think, the beginning of my PhD. And some of this work, as we go along, you'll see we have been enriched with input from all of them as well. So first of all, one of the studies we'll be looking at is how we explored, as I mentioned before, how we explored if the different ethnic name characteristics have an impact on the string similarities we receive when we attempt to do linkage on large population datasets, or basically do string comparison functions perform differently for different ethnic categories when we try to perform linkage in very simple terms. We were motivated by the fact that in most record linkage applications, we of course end up using personal information of individuals. And one of the most common and crucial operations in that process is to compare names. And as we all know, names differ diversely, are very diverse for different ethnic populations. So for example, a name from Sri Lanka is going to be really, really long, whereas other names or names in this part of the world could probably be of shorter length, could have different characteristics, could have different frequency distributions of characters, so on and so forth. But at the end of the day, we end up using pre-agreed or available string comparative functions that we are familiar with. And in this study, what we try to do is explore if these string comparison functions actually work fairly or similarly across the different ethnic groups. So some things we have to focus on when we also choose string comparison function, or that we often end up doing, is looking at the variations of them, and we try to accommodate the errors and whatnot when we try to evaluate if two names do refer to the same individual or not. And in doing so, as I mentioned, something that we have not been looking at a lot is how ethnic bias can play a role in the linkage outcome. So our research question when we're looking at this study was to see if the commonly used string similarity functions behave uneven when applied to names across different ethnic groups, and to see if it does introduce bias into the linkage outcome that we get. So how we did this was we relied on a good old NCVR data set that we often use because it has a rich volume of data as well as a very diverse data set. What we did is we identified a particular period within which we had bi-monthly snapshots of their voter registration database. And we identified all the voters who are common across all of these snapshots, which means using their voter ID, we knew that these voters were a true match across all, these voter IDs had a true match across all the different snapshots. And in doing so, when we compared all of these voters who were common across all the snapshots, we identified the voters who had variations in their names across the snapshots, which means that my name, Sumayya, in one snapshot could have errors in other, could have different variations or errors in the other snapshots. But still, the ultimate intention in performing linkage is to be able to identify that despite the variations, we are the same person. So we opted out, we removed all of the exact matches. We retained only the name pairs which had variations in it. In doing so, we identified close to 66,000 first name pairs and over 300,000 last name pairs with variations. And then we explored to see which ethnic category or which ethnic group did each of these name pairs belong to. So to do this, the NCVR dataset has an ethnicity flag. It has a race flag and an ethnic category, which we used. Actually, although we refer to it as an ethnic group, the NCVR dataset classifies it as the race. So, but also at the same time, there were certain names, for example, in this, like we talk, Ivan, might have variations in the name and might get selected during the sample process, but they may be assigned to different ethnic groups because people from different ethnicities have the same name. So that wasn't really contributing to our study of identifying if for different ethnic groups, the string comparisons perform differently because the same name occurs across different groups. So what we did was we identified or sampled only the name pairs which predominantly belong to a certain ethnic group. So we set a threshold. So for example, if we had white, black, Asian, and grouped other ethnic groups, we extracted only the name pairs that predominantly occurred in 80% within the same ethnic group. So for example, Priya occurred in 90% of the within the Asian ethnic group, in which case that was a name pair we retained. But once again, Ivan, since it occurred with a very low frequency, but across multiple ethnic groups, we didn't retain that name pair because we couldn't say that predominantly this belonged to certain ethnic groups. So we couldn't say that is why it performed better for this or not. So once we selected those name pairs, we performed the string comparison or compare these name pairs across all true matches using 4 different string comparison functions. The first was the edit distance, the second was edit text, the third was qgram, and the fourth is Jarrow-Winkler. So edit distance basically looks at the single character changes that you need to do to transform one string to another. Edit text transforms a bit beyond that. It looks at similar pronunciation. Qgram similarities look at splitting strings into substrings. We often rely on 2 characters. So we split strings into substrings of 2 characters, and then we calculate the dice coefficient between the sets we generate. And then we have Jarrow-Winkler, which calculates the similarity based on the number of characters that are common between 2 strings, as well as the number of transposed characters. So for all of those name samples that we extracted, we performed the string comparison using all of these 4 different string comparison functions. And then we tried to explore how the similarity distributions across the name pairs differed for the different ethnic groups. We explore results in two dimensions. First, we look at how, for a particular string comparison function, how the string similarity distribution differs across the different ethnic groups. In this slide, you'll see the first four plots on the left look at the first name distributions, whereas the other four plots on the right, of your side at least, looks at the last name distributions. So the cumulative distribution function basically tells you that at a particular similarity, which percentage of name pairs had at most that particular similarity value. So one thing that we see when we look at all of these plots is that the orange line, which refers to the white ethnic group, has a left shift, which means that for both the first names and last names, the white ethnic group has lower similarities in comparison to the rest of the ethnic groups. It's important to remember that all of these are once again true matches because we extracted the true matches across the different snapshots. But at the same time, it's also interesting to see that the Q-gram dissimilarities, which is this spot here and also this spot here, has an high elevation at the 0.0 similarity value, which means a lot of the true matching first name and last name record pairs have for the white ethnic group have a 0 similarity, which indicates that once again, the white first names and last names largely vary in comparison to the other ethnic groups. And another dimension we explored these results was in seeing for individual ethnic groups, how does the similarity distribution vary across for the different similarity functions? In doing this, what we tried to explore was if any particular similarity function gave very high similarities or very low similarities in comparison to the other, because this indicates that in general, when we do approximate matching, our linkage process is dependent on a threshold, and any outcome from this would feed us insights into how this threshold has to be adjusted. If this performs similarly across all similarity functions, chances are you probably could use a single threshold, but if it varies, that means according to the similarity function you choose, you'd have to defer your threshold once again as well. So when we're looking at this, we can see that specifically the Jaro-Winkler similarities distribution we get from using Jaro-Winkler has a right shift across all the different different experiment setups or different ethnic groups, which means that in comparison to the other similarity functions, once again, Jaro-Winkler gives us higher similarity values. So if you end up using Jaro-Winkler to identify matches and non-matches, you could potentially use a higher threshold value than you would be using otherwise. So one thing that we have looked at is that one thing that we see when we look at all of these outcomes is that definitely the different string comparison functions perform differently for the different ethnic groups. So when we are looking at a large population, chances are you potentially would not be able to do with a single similarity comparison function or considering all of the entire population as one. To look at how different this can be, this is another visualization that we did. Basically, we are looking at the recall values we get for different thresholds across the different ethnic groups. So we've highlighted in bold, we've highlighted values which we think are more insightful or contribute to understanding that this performance different ethnic groups. So if you look at 0.9 threshold, as you can see for the Black ethnic group, Jaro-Winkler achieves an 87.2% recall. That means if you set the threshold for 0.9, Jaro-Winkler identifies 87.2% of all of the Black name pairs that belong to the Black ethnic group, whereas for edit distance at the same threshold, it's going to capture only 9.4% of the true matching pairs. At the same time, if you break it down from a particular comparison functions, for example, if you look at edit distance, once again, the threshold affects significantly because at 0.9, you would get 9.4% of the Black true matching pairs along with the Black ethnic group, whereas as soon as you reduce it, it's going to increase to 83.8%. Similarly, you can see significant variations across other string comparison functions as well as ethnic groups. Once again, is why we decided to further explore how this could change across for when you're linking large databases. Another thing that we wanted to highlight here was that specifically, at least as of now, in applications that we've seen, we look at an overall evaluation measure. So, for example, in this table, you could see that if you were to not look at the different ethnic groups individually, achieving a recall of 0.91 would seem very high. But when you break it down across the different ethnic groups, you could say that it is not as high as for all groups, as you could see from single measures. So for the group others, you achieve a recall of 0.75, whereas which means that you potentially need to tweak how you try to match unique pairs from those ethnic categories when you're trying to perform linkage. So looking at these results a bit more, we came up with a couple of recommendations. First one was that specifically when you're linking large heterogeneous databases, it is important to investigate the diversity of the individuals or within your population. And for one, we know that certain databases have an ethnic flag, but alternatively, something that you could rely is the country of birth because our names are potentially linked to our origins, as a result of which our country of birth could provide a bit of information as to our backgrounds. Secondly, it's important to identify or understand how the different string comparison functions work across the different, and to identify string comparison function that works for your database or the diversified community within your database. As we saw earlier, Jara-Winkler seems to perform differently across the different ethnic groups, and similarly, Q-gram-based methods give you very low similarities in comparison to the other string comparison functions, and so you need to accordingly tweak. It's also important to see how last name changes occur across ethnic groups, because our results show that the white ethnic group seems to have a large proportion of last name variations in comparison to the other ethnic groups. And of course, it's important to adjust and calibrate similarities, as we saw, because the thresholds could make a huge impact for what you capture the recall across different threshold groups. And finally, to assess linkage quality by using stratified sampling of record pairs across the different subpopulations within your community. To what extent it could be done in practical application would, I think, once again rely on your application. But yeah, that's it, focusing mainly on our work on the performance of different string comparison functions for ethnic groups. I think we could do questions before we,
Yeah, we can do questions now. Maybe stop sharing so we can see the hands.
Yeah.
And we have a question in the room.
I can start off with one.
Yeah.
I was curious, do you look at things like string length for the different ethnic groups, for example? And I was a little bit surprised, I guess, that with the white ethnic groups you're seeing these.
Yes.
I was wondering whether,
Yeah. So to directly answer your question, no, we did not look at the specific characteristics of the name. We just matched the ethnic group to the name itself and let it run as it is. But that's one thing we intend to explore, because from sort of like a technical point of view, we know that set-based similarities such as Q-gram sets would potentially have a huge impact by the length of the name values or the string values itself. So we understand that it's those very same characteristics that result in the different string comparison functions performing differently across the ethnic groups, but we haven't particularly drilled down into what characteristics impact it yet, but that's something we can intend to do. Yeah.
Thank you.
And it is almost uniquely white names that are demonstrating these characteristics, not general white names. So we're talking about the subset of names that are 80% only appearing in the white ethnic group. So. Okay, any quick hands from the online people? Okay, if not, then shall we move on to the next bit?
Yeah. Yeah. Certainly, we Secondly, I thought we'll discuss some work we have done on a new evaluation measure for evaluating the record linkage outcomes.
Sumayya,
Yes.
don't forget to share. Joe,
Oops, sorry.
Thank you.
Did that work?
Yep, perfect.
Okay, yeah. So to take a step back, record linkage, we basically look at different pairs of records and we try to identify if they're a match or a non-match, and potentially in most practical applications, there could be a potential match, which we go on to clinical review, which is a conversation of its own, so I'm not going to step into that. But looking at generally from an application implementation perspective, you either have a match or a non-match, and the evaluation process would depend on how well your classifier was able to classify the true matching pairs as matches and otherwise. If ground truth is available, we can consider this to be a binary classification problem. But the important question is, even if you do have the ground truth and even if you know your classifications, how would you evaluate the performance of your classifier? If I were to ask what measures you all have been using, I think a majority of us would fall back onto this, the good old confusion matrix, where we look at ground truth labels and your predictive labels and identify which of your true matches are correctly classified as matches or otherwise incorrectly classified as non-matches, and vice versa. So I'm not going to go into all of the 4 boxes, but assuming that we have a fairly good idea about how the confusion matrix works, at the end of the day, we have 4 classes of true positives, true negatives, false negatives, and true negatives. And using these, we fall back on to 3 now for crisp measures that we often see in literature, which is precision, recall, F measure, and F star. But downsides, at least that we have identified with using such measures. For example, if we were to look at this table, we assume that there's a database containing 1,000 record master patient index records with no duplicates to be linked with 1,000 other health transaction records. We assume that there are 900 true matches across the 2 databases, and we assume that this classification of matches and non-matches has been done using 4 classifiers A, B, C, and D. Within the brackets, we have the number of true matches, number of matches that the classifier has identified, and of which we show how many of them are true positives, how many of them are false negatives, and how many of them are false positives. So using these numbers, we go back and we calculate precision, recall, and F measure. One thing that you can identify, at least from the numbers here, is that different classification outcomes can give you the same value for the different measures. So for example, although A, B, and D have a different set of classification outcomes, they have the same precision value, whereas B and C, once again, have different classification outcomes, but give the same F measure value. So looking at the individual F measure value or precision value or recall value, or precision OF measure value would not be very insightful in telling you how it performed across the different classes. So, and also another important aspect of that is a confusion matrix is dependent on a single threshold. So before you do any of the evaluation, you need to be able to justify the threshold you choose. But once again, as we discussed previously, the threshold is very sensitive and it could starting to differ across the different applications that you implement this on. Stepping out of those evaluation measures, there are also averaging evaluation measures like the area under the precision recall curve and also the H measure. In addition to that, I think there is recent work in partial area under the precision recall curve as well. Mostly comes from medical domain, if I'm not mistaken. But then in using such measures, I think one of the main issues is, once again, which range of similarity thresholds are you going to use in calculating for example, area under the precision recall curve? That's once again a decision you either have to make ad hoc or you need to be able to start and justify. So based on these issues, something that we wanted to do was to design a practical method that allows you to fairly as well as transparently compare the classification outcomes so that someone would be able to look at that evaluation measure and tell you if your classifier is good or across different classifiers, which of them performs best. And as we all know, this once again is dependent on the application, because for certain applications, a certain number of true positives might be okay, whereas for certain applications, true positives might not be okay at all. So it depends on the application. So stemming from that, what we thought was that we would try to design an evaluation measure which has an error tolerance. So it allows a certain number of false matches, and false non-matches are considered to be okay. And within those boundaries, within that error tolerance boundary, how can we evaluate the performance of the classifier? That is what we wanted to do. So we define an error rate, which in this we represent using epsilon over the rest of the slides. And we assume that the classifier the classifier is evaluated if its classification outcomes are less than this error rate. So both the false positive rate and false negative rate has to be less than epsilon. In doing so, let me take a step back and explain with this picture, diagram, which I think would mean a lot, which will make it a lot easier. So when you have your classification outcome, you know, if with your ground truth, you know which of them are true positives and which of them are false negatives. So basically, we have an error tolerance. We say that if we take the false negative rate, so for example, that means everything is in all of the true matches are incorrectly classified as non-matches. We start from a threshold of 1.0 or greater than 1.0, because in that case, the threshold is greater than 1, everything is initially classified as a non-match. And then we keep dropping the threshold. In dropping the threshold as such, we would hit a point, a threshold value, which is the first instance in which we step into the error tolerance boundary for the false negative rate. And that we classify as the upper threshold. Whereas on the other side, since recall is monotonic, this is going to keep dropping until it gets to 0. Whereas on the other side, we also can calculate the number of false positives that are classified. And when you keep dropping the threshold, you hit a point where you first enter the boundaries of hitting that particular false discovery rate. So that ends up being your lower threshold. So this area between the upper threshold and the lower threshold is what we consider when evaluating the performance of the classifier. So basically, when we look at so this performance measure is once again is built on a CRISP measure, but once again the underlying CRISP measure can be different. But for this moment, we consider the F measure. So what we do is within these boundaries of the threshold values, the upper threshold and the lower threshold values, we calculate the F star measure for each of thresholds within these boundaries. And the curl measure, or the consistent record linkage evaluation measure, which we call the curl measure, is basically the product of the average of the F star values within these boundaries and the difference between the truth thresholds. So to summarize, in looking at this, one, we only consider the thresholds that are within that perform within the accepted error tolerance rate. And two, we calculate the measure using an underlying CRISP measure, in this case, we use the F star measure by averaging that value across the boundaries. So basically what this tells you to interpret this, how this interpreted is it tells you what are the upper threshold and the lower threshold values within which this error tolerance can be met. The larger the difference between the upper value and the lower value, that means your classifier is robust. Whereas if your classifier performs within that error tolerance rate only at a very small threshold range, that means it performs well only at that point. So what we would technically like to see is a larger variation between the upper threshold and the lower threshold, which means your classifier is robust across the same. So we evaluated this using both synthetic and real-world data. So for synthetic data, we generated different data sets, where basically for a perfect data set, we had all of the records, all of the true matching record pairs within the perfect data set had a 1.0 similarity, or was 100% were an exact match, whereas all of the non-matching record pairs had a 0 similarity, so were entirely different. So the excellent data set, 95% of them were an match, and the other 5% of the true matches had slightly lower similarities, and so on and so forth. We kept dropping the quality of the data, or the quality of the true matches and non-matching record pairs. In doing so, as you can see, since all of the true matches have a perfect 1.1 similarity score, and all of the non-matches have a perfect 0 similarity score, the classifier is going to be robust across all of the different thresholds. Whereas when the quality between of the quality or similarity between the true matching record pairs and non-matching record pairs start to differ, then the classifier begins to become less robust across the similarity thresholds. So now in the second instance, in the excellent dataset instance, the classifier is robust only between the 0.67 and 0.93 threshold range. This is one of the real world data sets that we got from a data repository. And in this, what we would like to highlight is that although the CRISP measures such as precision, recall, and F-star give you very high values, the curl measure, on the other hand, tells you very clearly within which threshold ranges does it actually agree on the accepted error tolerance. So that means if you move anything beyond these thresholds, you either hit more false negatives than intended, or you hit more false positives than intended. So in this work, we basically introduce a new evaluation measure, which basically is dependent on an error tolerance rate. And in doing so, what we wanted to do was move away from the CRISP evaluation measures, which are dependent on a single threshold value, and explore how we could evaluate the robustness of classifiers against different against larger ranges, and to see if we can have a more understanding of how the classifiers performed in different settings. Yes, I think we can do questions.
Great. Thank you, Sumayya. Let's do the bit of dance.
Yeah, sorry.
Stop sharing again. Good. Questions?
If that made sense.
Yes, Mike.
Hi, Sumayya. I really enjoyed the CRL kind of concept. It's really good. I had a chat before about at the moment you just take the average between the upper and lower, the
Yes.
F-star. Is there anything, do you think, in terms of the shape within the actual curve within the those two bands, not just the average of it?
That is not something we have thought about at the moment. But now that you mention it, yeah.
Okay, cool. And a follow-up question, just because I noticed that some colleagues are online who might be interested. Have you thought about how this might be used for, because it's specifically you can compare between models and look for like drift and things like this.
Yeah.
How you might, could this be used for model optimization and monitoring drift and things like this? I'm just thinking as a target function, can I optimize a linkage model to get the best CRL score it could?
So that is going to be dependent on the error tolerance that you introduce, right? In which case, I think optimizing the measure itself would mean that you would tweak the error tolerance of your application. But otherwise, how? Yeah, no, I think it's going to be dependent on the error tolerance that you introduce, and tweaking that is probably how, yeah. Unless Peter has other.
No, it's just interesting because it's quite a different way of thinking about the performance metric, right? Here you're saying what is the user comfortable with, and working towards that. So I do like it as a metric. It's quite nice. Yeah. Thank you.
Great, thanks, Mike. Can I ask a question,
Yeah.
Sumayya? So my understanding of CRL is it's concerned more of the performance of the model,
Yes,
and less concerned of the performance of the linkage.
yes,
If you can separate the two.
yeah.
So I hope I'm asking this on behalf of my applied researchers. How would you explain CRL to someone who's using the downstream data and helping them make sense of the linkage?
Well, interesting. Well, I'd rather look at it as something that someone who generates the linked data would look at to evaluate if the classifiers they're using or the process they have in hand is the best one that they have, or if they are choosing the right classifier. I tend to use the word classifier a lot because I come from a technical, or rather to say if the choice of classifier to generate that particular data set is the correct one, is what curl would help you do. But that, of course, from downstream perspective, would probably be useful to boost confidence in the data you have in hand. But I think it's not something that the downstream user is going to end up saying at the end of the day. If that makes sense.
So my thoughts are quite similar to Mike's around it being quite useful for benchmarking and helping us understand what have we done so far, and so how much more can we improve in terms of the model building, or like improvement could come from data quality improvements, right? And not specifically around.
Because I think at the end of the day, curl looks at what you have in hand, and it cannot improve the linkage outcome itself. It's basically evaluating the linkage outcome. But to improve the linkage or to improve the quality of the data you have in hand, the only thing that you can tweak in evaluating that is the error tolerance. But that, once again, is just a number. If at all anything else that flows into it has to be from before.
Cool. Very nice. Good. Any other questions online in the room? Good. Shall we move on to your historical linkage?
Yes.
Don't forget to share.
To share this screen.
Joe's hidden the share.
Okay. Hope that worked.
Yep. We've got there we go. Thank you.
All right. So this is more of a practical application of linkage, a bit different to the theoretical stuff or the technical algorithm designing and stuff we do, or at least I do in my PhD. So this is based on work we did once again with the Scottish Historic Population Platform, the SHIP project, that I had the opportunity to collaborate with for about a 6-month period. And where I actually got to apply what I knew of theoretically before in a more application perspective. We have a running joke about this that I should not talk about what I should not be talking about. So I hope I do not talk about what I should not be talking about. But yes. So the SHIP, Scottish Historic Population Platform, or rather SHARE, database basically consists of digitized records about births, deaths, and marriages that happened in Scotland from the years 1855 to 1973. The births, deaths, and marriages, or their certificates, we refer to them as vital life events, and we have got about 25 million certificates in total spanning across these years. So each certificate contains personal details about individual people, and we refer to them as actors. So, for example, a birth certificate would have information about the birth child or the baby and its parents. The marriage certificate has information about the bride and groom and their parents. And a death certificate would have individuals about the deceased and possibly information about their parents as well as their spouses. So all of these certificates, of course, from olden times, have been transcribed, and during the process, we know that there's a visible loss in quality by reading the certificates manually and then entering them into a digitized system. So basically, if you have, there are certain policies in place in transcribing them, that basically unreadable words are often represented by a hash value, and any unreadable characters are referred to using an @ value. So basically, this name, this string value could refer to either milli or tilly, because you don't truly know what that missing @ character refers to. The intention of the SHIP project is using all of these vital life event certificates to be able to reconstruct the historical population of Scotland over time. Interestingly, they also have access to another database, which is census records. Census records basically are snapshots of the population within Scotland at that particular time when census were recorded, and they were collected at certain intervals. So we have access to the data from the Isle of Skye, and the census have been collected once every 10 years between 1861 to 1901. So we've got census snapshots, 5 census snapshots across these periods. All in all, we have about 32,500 vital life event records and 86,500 census records for the Isle of Skye area. The census records are a bit different to the life events. The census basically tells you that at that point when the census was collected, who was residing in that particular address. So we have from families to servants to visitors, people who are passing by, all of them at that particular location were recorded in the census. So what we were looking at in this particular work was to see if we are able to successfully link census records at that particular time to vital life events occurring around the neighboring time period. And in doing so, what we wanted to see was if we could evaluate the trends, the geographical trends, or social trends across amongst the geographical boundary. So linking these vital events to census gives us insights about how the populations change over time, migrations both inwards and outwards, fertility, mortality, and so forth. So we explored how record linkage techniques can be adapted to integrate these records, these different data sets that we have in hand, with a particular focus on the birth, marriage, death, and them to the census records. So we adapted different types of linkage techniques, but specifically we looked at births, marriages, and deaths separately. We looked at linking birth babies to later census individuals. We looked at linking brides and grooms to their previous census, as well as census post-marriage. And then we also looked at linking the deceased to the previous census to see if we can identify correct links between people in this population. We explored both exact matching and approximate matching. So for exact matching, we expect that all of the particular attribute values that they're using for linkage are the exact same and could have no variations. Whereas for approximate string matching, we allowed variations, and as we discussed from the very beginning, we used different string comparison functions, and also we looked at different thresholds and how the outcome varies across this. For the linkage setups, we also consider temporal constraints. So for example, for you to be married, we expect that we considered individuals above a certain age limit. And for babies, when being linked to census, once again, their years of birth had to match their particular records in their households. Unfortunately, though, one significant issue that we came across when doing this work was that we had very limited ground truth. So all of our evaluation outcomes or the evaluations that we look at in the rest of these slides are dependent on the very few ground truths that were available for the population. So we looked at linkage using names primarily. So for the primary actor, which is the baby for birth, deceased for death, and the bride and groom for marriage, we looked at generating keys for the primary actor using the names, the particular individual's first name, surname, as well as the parent's first name. And for all of the individuals in the vital life event records, as well as the census records, we generated this same key. And then we also looked at the different data we had in hand. So we had the original transcribed data, and we also had standardized data. So standardized data were basically the name values cleaned by domain experts. So we saw a significant difference in the outcome in contrast when we used the original data versus standardized data. So in addition to building the key with the names, we also explored the usage of other attributes, the year of birth, as well as the registration district in which the vital life event certificates, as well as the census records were registered. So these are going to be a lot of numbers, but I'll just run through it for you quickly. So we look at the outcome for the different linkages separately. And we also look at how the linkage outcome varies for when you use the original values, original name values versus the standardized name values, versus also how the linkage outcome differs when you do exact matching versus approximate matching. So interestingly, we get very high precision across the different setups, as you can see, but recall is very low when you use the original values. But once the values are standardized, or the name values are standardized, we see a significant increase in recall. It's not as high as precision, but at least we know that with the precision values, that a majority of the true matches that we classify with high confidence possibly a true match. At the same time, when we do approximate matching, on the right side of the screen, you might see that we've shaded certain numbers. The numbers in blue, which we have shaded, imply that there's a significant improvement in recall in comparison to exact matching, whereas the numbers we highlight in red show that there is a drastic drop in precision in comparison to when we do approximate matching. So this is a pattern we have seen across all three linkage setups. This is when we link births to census. This is when we link marriages to census. Unfortunately, for both marriages and death, we see very low numbers, but this is also primarily influenced by the fact that we have less than 10 certificates for which we have ground truth in most cases, in which case even a single misclassification or two can make a huge impact in the classification outcome we see. But once again, precision is considerably higher for most of the setups, whereas recall is not as high. And we see the same when we link the deceased to previous census as well. So this has actually been an interesting application that I personally came across because it was a lot nicer to deal with actual in-person data. But what we saw was that even exact matching techniques can actually be useful in linking historical vital life events. We do know that recall is low, but precision seems to be very high. Birth and marriage certificates generally offer better quality than death certificates. This also probably due to the fact that when you're deceased, it's someone else who's filling in your information on behalf of you. And it's also important to identify, as I think in any linkage application, to identify the most informative set of QID attributes that you could be using for linkage. We also noticed that standardizing values significantly improved our outcome in comparison to when we use the original name values. But also approximate matching does improve recall in certain setups, but in at least this setup, we noticed that exact matching alone itself performs a lot better, with approximate matching only showing a slight variation in the outcome. So at the moment, as I mentioned, we've only been working on the Isle of Skye data set, but in the near future, we hope that we will have access to work on the more modern data and to look at how this varies in a much more larger scale, as well as how the outcomes will differ. Something else that we are also considering is looking at linking sibling bundles across both births and census to track families there. Yeah, that's it from this. Any questions? Sorry, just gonna.
Good. Thank you very much, Sumayya. Let's see if we got questions online. Oh, yes, Nuri.
Hello. If you don't have any questions in the room, I'll jump in. But
Yep, go ahead.
yep. So have you looked at what sort of cohort you can create where you might see people being born and dying and possibly getting married, but not everybody might get married?
So we actually have not explored that in detail, but certain things that we have, unfortunately, one thing that we have is most of the deaths that we have in hand, at least for Isle of Skye, are those of children and infants. So when we try to do a complete end-to-end linkage, even from birth, marriages to death, there are very few links that we are able to create. But I think that would potentially change once we have much larger data sets in hand and possibly also richer ground truth. So in which case we could potentially explore those avenues as well.
Thank you. That's fascinating. I wondered if, once you stitch them together, you can correct some of the data to then do a second iteration of matching. But thank you. Very fast, very interesting.
Cool. Other thoughts? I think we can take one more question. Well, I'll jump in for now. Sumayya, could you share your insight about how could the modern linkage designers take a page from your work? I think what we don't usually do is to take into account of relationships, marriages, mothers and babies, and we often use that as a post hoc way of identifying relations as a product of the linkage rather than relying on the relationship as a flag for particular diets or clusters of records. Wondering if, so it's almost a chicken and egg problem. Whether you believe that to be true to base your linkage on, or whether you first link your data, then derive those relational information from. So
I think in our case, actually, the relationships help enrich the links that we create. But then also, once again, I think the way of the society back then and now would potentially play a huge role as well. And then the impact it has could potentially differ. But in our case, certainly having that additional information about, for example, the demarcations of a household from the census that let us know the number of people in the family, or even things like that, are pretty insightful, informative when trying to identify the links. But of course, I think in this day and age, I don't know to what extent, the ways of life and everything will affect it. But,
it's a thought. Good. Questions online? Good. If not, I'm sure you all join me in a big round of applause for Sumayya for showing us several different key work from her PhD. And I'm sure Sumayya wouldn't mind sharing her contacts as well for any further questions in any piece of work. Just a quick shout out to the feedback form that you would see in the chat as well. To complete the feedback form, share your thoughts, topic suggestions on how we would schedule our next ITALO webinars. But that's all from us today, and thank you all for attending and keep on engaging with our networks. Right, see you everybody.
thank you.
Thank you.